This is for 1.3 and 1.4. So there are a few terms that we need to be familiar with. If you guys remember, last Friday we were talking about mole fraction, in which you just had to find out the moles of whatever element was given in the question, uh, divided by the moles of the compound, and that was a mole fraction. Now this is something similar, and the name tells us that it's meant to be a percentage. Now before we talk about percent composition, I'd like to remind you guys about the law of fixed proportions. This means that there should always be double the amount of hydrogen in water in order for it to be water. If it's not H2O, if it's not a 2-to-1 ratio between hydrogen and oxygen, it's not going to make water. So this is the law of fixed proportions. You don't have to know this, but you should know the purpose behind it. So percent composition would be the molar mass of just the element divided by the molar mass of the compound. Now I could give you any compound here. For example, it could be butane. The formula tells us that 4 carbon atoms bond with 10 hydrogen atoms. In order for nature to make butane, this is the ratio that we're gonna need. Now obviously, because I'm saying ratio, I can say that it's a 2-to-5 ratio. I simply simplified it in my head. So I could ask you the percent composition of carbon in butane, and what you would do is that you would just take the molar mass of carbon and you divide that by the molar mass of butane and multiply that by 100. Empirical formula units are just the simplified molecular formula that tells us the ratio. For example, for butane, I just told you about the ratio. Some compounds like sodium chloride and water, they can be further simplified, so their molecular and empirical formula would be the same. These are a few examples over here. So the molecular formula tells us that in order to form a unit of benzene, 6 carbon atoms are going to have to bond with 6 hydrogen atoms. Now if you simplify that in order to find out the ratios only, that would be 1 part carbon and 1 part hydrogen. That is the empirical formula, and you guys can go through the rest of them on your own. Now, how do we calculate empirical formula? So let's look at this question. This is also available on AP Classroom. A compound was analyzed and found to contain 13.5 grams of calcium, 10.8 oxygen, and 0.675 grams of hydrogen. What is the empirical formula of the compound? So we do know the elements that are present in this compound. It's calcium, oxygen, and hydrogen. But we want to know the ratios, okay? So remember, the rule of thumb is to always convert to moles. This should be a habit that you adapt throughout the year. So let's see, I have 13.5 grams of calcium. I'm going to figure out how many moles of these elements I have each. I simply multiplied them with their molar masses I picked up from the periodic table. Remember, the periodic table is going to be provided to you on the test, the main exam, and even the test that we have throughout the year. And then once we have all the moles, we divide them with the smallest numbers out of these 3, out of whichever elements you're dealing with. So here, because 0.337 is the smallest, look at how I divided all of them with 0.337, and I got these numbers. Okay, now because these are already whole numbers, we don't have to do anything else. If these were not, if any of them were not whole numbers and we couldn't have rounded them up very easily like this, like if they were 3 or 4 numbers apart, I would have thought of a common number, I mean a number that I would have multiplied all of these three with, but we don't have to do that. So now I know that I have 1 part calcium, 2 parts oxygen, and 2 parts of hydrogen, and this is exactly what we wrote here. Now it's okay if you want to leave it like this. Nobody cares that you converted it into this, as long as the ratios are correct. You are not further tested on writing the usual way of writing the formulas. And also, you don't have to worry about writing oxygen first, calcium later. It again does not matter, as long as you have the right ratios. Okay. Now, this is another question. It's the same thing. It's asking you about the empirical formula of a compound, only that they've given you the amounts of the elements in that compound in percentage form. In the previous question, they gave it to us in grams form. This is just a trick. You have to do the same steps, only that you would assume that because it's a percentage, it's out of 100. So you could assume that you have 100 grams of the compound, and out of that 43.6% is phosphorus. Okay, so this is why we just replace the percentage with the grams unit. We follow the same steps. Please look over here how once we divided these with 1.48, considering they're the smallest number out of these two. Notice how I get a 1, a whole number here, but here I get a 2.5. Now, mathematically, I know what we've learned is that if the number is anything above a 5, we can round it up to 3, but that is not what we're going to do here. It should have been at least a 2.8 in order for me to have just rounded it up to 3. I can't do that because it's a 2.5, and ratios cannot be, or formulas cannot be played with by just adding up, that amount of the elements. So what I'm gonna do is I'm gonna multiply these numbers, one mole of phosphorus and 1 mole of oxygen, with 2 or any number that would give me whole numbers. Okay, so that's why I multiplied it with a 2, and now I have whole numbers. These are a few exercises. You don't have to do them. I would recommend that you jump to 1.3 and 1.4. This is also something similar. Again, you have percentage. It doesn't matter. You just need to assume that it's grams and it's out of 100. They have further asked us to find out the molecular formula. So we're not stopping at the empirical formula, in which we have figured out the basic the ratios between carbon, hydrogen, and oxygen. I want you to pause and read the question. Okay. Now, once we're done with figuring out the empirical formula, in a question like this, we are always given the molar mass of the molecular formula. And after all the steps, when we have the empirical formula and we find out its molar mass, we see that it's around 30 grams. That's 12 for carbon, 2 for hydrogen, and 16. And they have told us in the question that the molar mass should be 180 grams, not 30 grams, which is what we're getting from this simple ratio. So all we have to do is think of dividing the number 30. We have to think of a number that if we multiply with 30, we would get 180. And that number is 6. So we multiply the whole formula with a 6, and that's how we got C6H12O6. All right, that would be it. I'd recommend that we immediately jump to 1.3 and 1.4, I do, we do, you do. Also, let me go through one of the questions in 1.4. So in the first part of the question, we have to balance this, okay? And once we've balanced it, they want to know the mass of oxygen that was in the sample. Now, they have told us that aluminum and aluminum oxide, we have 120.91 of aluminum and aluminum oxide, and the total mass is 120.32. So that means that whatever you remove out of 120.32, if you remove 120.91 out of it, the remainder would be oxygen. So that is how we got oxygen. Now in part C, I want you to go through the steps of this. The thing is that this is also related to one of the later units, so I don't want to focus on this. Basically what we've done here is that we looked at how many grams of oxygen we had. We converted it to moles, and once we had the moles of oxygen, we want to know the mass of aluminum oxide in it, which is Al2O3. And just like conversion factors at money exchanges, we have to look at the numbers that we have here, the conversion factors here. And this balanced equation tells us that every time we have 3 moles of oxygen, you have figured out for 1 mole of oxygen, okay? Every time we have 3 moles of oxygen, we have 2 moles of aluminum oxide. And this is what we used here. 2 moles of aluminum oxide over 3 moles. That's just you trying to convert from PKR to US dollars and then Saudi reals or yen or whatever. And then we simply found out the moles of aluminum oxide, and we converted it to grams again. But it's okay if you were not able to figure this out, because I'm going to get into the details of this in one of the later units. All right, thank you.